Continuing with liquid properties, we want to talk about vapor pressure. Before we get to vapor pressure, we need to define what a vapor is. So if we remember, liquids are defined by all the molecules are touching each other, but they are freely moving, right? They're all moving around, flowing on top of each other. So if I have, say this surface of the liquid, I could draw like a surface like that, kind of the liquid, and there's going to be molecules moving around. And some of those molecules will be moving a lot, and they will end up escaping from the liquid into the gas. And these escaped liquid molecules are called a vapor. So one thing, technically, in the world of chemistry, vapors exist above the surface of a liquid. So the gas that exists above the surface of a liquid. This happens for every single liquid. There are always molecules of that liquid that have escaped into the gas phase. Different numbers for different types of liquids, but there's always going to be some out there. And so this just naturally happens because the molecules are moving. If you think gas molecules tend to move faster than liquid molecules, but there's a distribution of liquid molecules. And so the high-end molecules, the ones that are moving real fast in the liquid, just kind of bounce around and eventually escape. They're on the high end of the kinetic energy, and they have enough to become a gas type molecule, move into that vapor phase. So vapor is gas above the liquid. So when you have this sort of escape of liquid, we call this evaporation. So this is something, if you take, say, a glass of water and you leave it out, those molecules are just going to keep escaping. They just keep escaping slowly but surely, and you get evaporation. Eventually, all your liquid is gone. Because if you have, say, a glass of water in a room, all of a sudden the entire room is full of vapor from that water, and that's quite a bit. In this case, they would go. So where it changes is if you, say, put a lid on it. So say you got a jar and you put a lid on your water or whatever liquid you have. And so what will end up happening is those molecules will go into the vapor, but some molecules from the vapor will go back into the liquid, right? Because these things are just moving around randomly, right? And so eventually one could hit the surface of the liquid from the gas phase, molecule could hit the surface and then stay there. Right? It could stay close to its other molecules and then rejoin the liquid and be in the liquid phase. And so this idea of, you'd have molecules come in and out from between the liquid and the vapor, and eventually you'll reach some sort of constant number of molecules in the vapor phase. What those molecules are will be changing because there's going to be constantly some molecules leaving the liquid and some molecules going back into the liquid. So it's going to be kind of a cycling, if you will, but there'll be a constant number of molecules. Constant number of molecules leads to the pressure of those gas molecules. So the vapor molecules in vapor will be exerting some sort of pressure, and we call that the vapor pressure. Now, it's important to note, for most liquids, vapor pressure is very low. Not a lot of molecules escape. The reason why water can evaporate is if you go from, say, an open glass, say, into a room that is, thousands of gallons of volume, that's just a really, really big space, and a small amount of molecules, you need a decent amount of molecules to still reach that low pressure for the vapor pressure. So not a lot of molecules are going to escape, but some always do. Every single liquid has a vapor above it, and the vapor pressure tells you how many molecules there are. More molecules, higher pressure. So how many molecules are in the vapor phase? It's based on the intermolecular forces. Surprise, surprise. So if you have a really strong intermolecular force, that means these molecules in the liquid do not want to move into the vapor. Right? The whole idea of moving into the vapor is molecules that are escaping the liquid. If there are really strong attractions to these other neighboring molecules, that will hold the molecule in the liquid. It won't go into the vapor phase. Or conversely, if one of these gas molecules, vapor molecules, collides with the surface of liquid, if there's really strong intermolecular forces, it's going to get stuck. And so what that means is you don't have a lot of molecules in the vapor phase. So stronger intermolecular forces lead to lower vapor pressures. Molecules would prefer to stay in the liquid where there are strong intermolecular forces. They're attracted to their neighbors. Conversely, low intermolecular forces lead to high vapor pressures. So do want to point out this is the first, all the other properties, viscosity, surface tension, boiling point, strong intermolecular forces lead to higher values. Vapor pressure is backwards because you're measuring the tendency of molecules to not leave for low vapor pressure. Not leave the liquid, I should say. And so we do, want to be careful. It is the kind of opposite day intermolecular force. So this vapor pressure is one of the more common actual properties we think about. So water, we know, has hydrogen bonding. So the vapor pressure of water is 31 millibar. So that's really low. Normal pressure is about 1,000 millibar. It's about 1 bar. Acetone, which is nail polish remover, only has dipole-dipole interactions, and its vapor pressure is 307 millibar. So much, much higher vapor pressure, about 10 times larger. And so what this leads to, this idea of vapor pressure, is the idea of volatility. And so volatile liquids have really high vapor pressures. And so what that means is that it's really easy for molecules to escape into the vapor phase, and they evaporate more quickly. So that's what volatile means. And so acetone is nail polish remover. It's a pretty volatile liquid, and what that means is that it has a really strong smell. If you've ever opened a bottle of nail polish remover, that smell hits you instantly because this bottle is closed, right? If you think about it, and there's just a pile of vapor in that container. And what happens is once you open it, all of those molecules escape. There's just a lot of molecules in there. So any compound that has a strong smell is volatile because a lot of those molecules are escaping. And this is what volatile means. It means the compound evaporates readily. You may remember there was the fire in LaPorte at the ITC terminal. And there was a lot of concerns about volatile organic compounds. And that word volatile, we're used to thinking means kind of explosive or flammable, but it really means they evaporate quickly. Why that tends to go hand in hand with flammability is if you have a bunch of flammable molecules in the air, it's really easy to get a good fire going. But volatile really does mean it evaporates quickly. And that's potentially dangerous. That's also why acetone, if it smells if you can smell it, that means those molecules are going inside your nose and potentially affecting you. So high volatility does mean we want to be careful. The gasoline's also highly volatile. You can smell it right away. Let's apply it to some compounds. Which compound has a higher vapor pressure? Cl2 or BRF? Just like before, when we're trying to compare a liquid property, in this case vapor pressure, to the formulas, we need to use intermolecular forces to relate those. We want to know that strong intermolecular forces leads to low vapor pressure. But we want to be careful because what we're actually interested in is higher vapor pressure. So in this case, we're actually going to be looking for what has the weaker intermolecular forces. Which molecule has weaker intermolecular forces? So what are the primary intermolecular forces for each of these molecules? What's the Lewis structure? So I got Cl2 and FBr. These are very similar looking molecules, just two halogen atoms with a single bond. But chlorine is the same atom, and so that is non-polar. So dispersion has to be the primary interaction. FBr, BRF is polar. And so that means dipole-dipoles can be my primary type of interaction. So we know that dipole-dipole is stronger than dispersion, or conversely, we can say that dispersion is weaker, right? For higher vapor pressure, we want the weaker one. And so that means chlorine, Cl2, has a higher vapor pressure. So if we had two liquids of these, the Cl2 will evaporate more quickly. That also potentially means that we need to be more mindful that the Cl2 is potentially dangerous. just because there is, say, a liquid, there are molecules leaving that liquid, going into the vapor phase, and potentially going into, say, your nose, your mouth, you breathe them in, your skin, your eyes. And so that's why we want to be mindful of anything that has a higher vapor pressure means we want to be careful with it. We want to have it in a lid, put a lid on that container because it will get out and go into the air. Okay, another question with no participation, another video with no participation questions. Got to watch more videos, looking for more questions on participation 116. See you in the next video.